Hey everybody, welcome back. Another term of school. GME 163 route surveying. I think it's a really fun course. It's pretty field intensive. There's a lot of field work, but this is a class where you actually get to design a route, design a survey, execute the survey, and then produce results in the form of a plat. So it's kind of putting the things together that you've learned so far in 161, 162, 175. And so a lot of the material you're expected to already have familiarity with, but this is sort of this is your chance to put it all together. So as an introduction, let's just quickly go over the syllabus. My name's Rob. You can just call me Rob. I'm super laid back with that. It's a laboratory intensive project. At the end of the course, you should be able to describe the role of the surveyor in route design. Understand the basic principles of topographic data for construction of digital terrain models. So digital terrain models are the topographic element, contours, elevation data that help you to incorporate your observations into earthwork calculations, volumes, area. You'll be using what you know about horizontal curves, vertical curves. So yeah, that. So a lot of topographic data. We're going to lay out a control network, and within that control network, we'll have vertical data, we'll have horizontal measurements for distance and angles, we'll have vertical angles. And then once we've collected all of our data, we'll be performing an adjustment, a compass rule adjustment, so you can get good coordinates on your data. And then when we have the adjusted control network, we'll be collecting our topographic data from our control points we're laying out and creating a TIN model, and then performing the calculations necessary to design our final route layout. Now, the first couple weeks, we'll be going over what a route is, what the components of the route would be, how we do the line offsets, the point offsets, those kinds of things. We'll be calculating areas and volumes, transition area. You can read through this list of objectives and sort of keep this at hand as we go through the course and check off the points that we're learning. So as a prerequisite, you should have had plane surveying 161 and plane surveying 2, 162, as well as the GME 175, the computations and platting. That's really important for the coordinate computations that we'll be performing. Text. The text is required. So I'm just going to pull it over here. You should already have this from your other courses. It's not a new text. This is the Galani and Wolf Elementary Surveying, and let's see if I can get the glare off there. This you should keep for the rest of your career. This is a text that I refer back to in my everyday work. It's really informative. It's really explanatory, but you'll be using this throughout the course. Now, we use the 15th edition in the class. Hopefully you already have it. You don't have to spend the money for a new textbook. But if you haven't already purchased it, you need to purchase it. The 15th edition is what we'll be working from. Now, most of the material is the same as what's in the 13th edition. However, the homework assignments are different. So when I assign questions out of the book, they're going to be different than the previous editions. If you're working from one of the previous editions of that book, please make sure you have access to the current edition so that when homework problems are assigned, you're doing the correct problem. I don't have a way of looking at, well, I do have some previous editions, but I don't want to try to recreate the wheel for, if I assign a number 13, you're doing a different number 13, it just doesn't work. So yeah, Elementary Surveying by Galani and Wolf. You want to get that. Other required materials, you'll need engineering grid paper. So all homework assignments are to be done on engineering grid paper, and that's the green grid paper, engineering paper with the little squares, the graph. Really helps with trying to scale your sketches. So engineering scale paper, drafting compass. And by the way, all of these, I provided a link to an example here, as well as in the email. Hopefully you all read through the email I sent out. I have links to Amazon products, which are suggestions. You don't have to get the exact ones that I sent out, but something similar will work. But a drafting compass, you've all seen these before for drawing circles. You're going to be using these for the sketches in your homework problems as well as the field notes. So let's see. I skipped the drafting or the engineering scale. So you're going to want to have an engineering scale. I have this little guy here, fits in my pocket. I really like it. I actually got this when I was a student OIT from the bookstore. It's aluminum and really hardy. You can throw it around, but it's pretty tiny, pretty useful. You can also get the big one, like what I suggested in the link. 90-degree straight edge. So hopefully you've heard the spiel. We don't use scales or rulers as a straight edge. The reason for that is that if you run a pencil or a pen along your scale, it starts to wear down the graduation. Also, you get ink and lead on your scale, which then transfer onto paper when you're drafting. Straight edges. So drafting straight edges. These are really helpful, particularly the 90-degree portion. Now I have a 45-degree straight edge. I also have a 30, 60, 90 straight edge. So these are really useful. Again, with the sketches on your homework, which we're going to go over homework standards in just a minute. You need to be able to draw straight lines. You need to use your drafting compass to draw actual curves. Otherwise, your sketches aren't going to come out very useful. Calculators. So I'm sure everyone's aware that Hewlett-Packard has discontinued the HP 35. That's really unfortunate because they're great to work with and program, but if you have one, please use it. If you don't have one, make sure you're using the calculator that's suggested for the department courses. Okay. Let's see, Carlson Survey, the student license. So I'm going to click on this link. Hopefully it'll work. Okay. So the student license, when you click on the link, it'll bring up this application. This is really, really generous of Carlson Survey. So they allow students to purchase for $99 a year-long subscription, or actually software download of their Carlson Survey, which is, I believe, the most ubiquitous drafting software for surveying in the industry. It's really useful. I really strongly suggest you download a copy It's nice to have the convenience on your own laptop or home PC when you can't get to campus. It's just really convenient, really nice. You really should consider going ahead and purchasing for $99. I mean, my license for my work costs about $1,700. So it's a great deal. A lot of students have asked me in the past if they could use Civil 3D, and my answer is sure. You can use whatever software works. I know that most of you have had already had a course in Civil 3D for engineering drafting. Civil 3D is a great product. Just be forewarned that I'm not familiar with that software and I don't have access to that software. So any of the work you do in Civil 3D, I really can't advise you on how to execute your projects. Maybe somebody on campus can, but you're really kind of placing yourself at a disadvantage by limiting yourself to just one piece of software, because chances are when you go into the industry, you're not going to be able to use the software that you're used to. Carlson works off of IntelliCAD, which is based on AutoCAD products. So a lot of the functionality is the same as Civil 3D. Try to work in Carlson if you can. That way we can all kind of help each other out and work together. So let's see, I lost track of my place. Okay. Finally, the field books. So Write in the Rain field books. These, I know we don't have a lot of rainy, wet weather down in Klamath Falls, but these are great field books. This is the 4.5 by 7. This is what most students use in the field work. You've probably already purchased this for prior labs. So for this course, you're going to want to get a new one. The insides look like this. They have a more of an accounting layout on one side and then graph on the other side for drafting. These are really convenient. They fit in your pocket, but they're big enough to keep notes on. All right. So those are the materials that you'll want to have for the class. And again, all of the links that I provided are suggestion only for the most part. The exceptions are the textbook, Carlson survey software, and the Write in the Rain field books. Well, that's kind of a suggestion. You can use something else if it works for you, but you will be making copies of your field notes and putting them in your folders, which you'll present to me. So grading. This course is designed to offer both theoretical and practical understanding of route surveying. I tend to focus heavily on the theoretical. My reason for that is theoretical understanding of the principles allows you to recall the information rather than just memorizing formulae. When you memorize the practical formulae and formats for performing a function, if you forget that, you're kind of sunk. So I like to teach a lot of theory. That way, you're going to gain conceptual understanding of how horizontal curves are laid out and where all of those functions are derived. I think that's a lot more helpful than just memorizing formulae without knowing where those come from. So there's, of course, homework assignments, and I mentioned we'll go over homework standard. There's going to be 1 or 2, probably not 3 midterms, but it just kind of depends on how the class goes. Midterms are a tool, exams are a tool to kind of keep you on track with your understanding. And then, of course, final exam, and then a final lab project. As I mentioned before, this is a lab-intensive course. So the whole goal is to get you to apply your learning to a final product that you could record with a county office. In this case, we're not actually constructing a road, but we'll be going through all of the survey applications for laying out and designing a route. All coursework is due at the designated date and time. Late work will not be accepted by prior approval of the instructor. That is without exception. So I do not accept late work. If something serious happens and you need to have a conversation with me about taking a hiatus from homework, we can have that conversation. This course moves way too quickly to fall behind. So if you miss a due date on homework, we're just going to move forward. Yes, you'll miss the points, but it's a lot easier than trying to catch up later down the road. So homework is due on the date assigned. When I assign homework, the due date will be clearly noted on Canvas. You'll be very clear of that. So let's see. Exams, sometimes things come up. Once in a great while, I've been known to allow an exam to be taken outside of the assigned exam date. Very, very rarely. So just consider that a concrete time. They are take-home exams. So I do 24-hour take-home exams. The exams will unlock at a specific time, then relock 24 hours later, at which time you will not be able to submit your exam work. This sounds like a good deal. Take-home exams always seem to be more desired than in-class timed exams. However, just know that take-home exams, because you have access to notes and whatnot, they're significantly more difficult. So, yeah, that's it on exams. Homework, we still have to go over standards, but again, assigned by the due date, or assigned with a due date. Late papers not accepted. All homework is to be clear, neat, legible, and in the format prescribed by the department. I've posted on Canvas the homework format. What I like to tell students is that we're preparing for a professional career. Probably in the past, homework has been not really that big a deal. You just put the answers down on paper, submit it. We're preparing for a professional course now, or for a professional career. I like to tell students, think of your homework submission as a presentation. You are walking an audience through the solution process and then clearly laying out your solution with justification. The solution, the process should be legible. All of the formula you use should be stated, and then explanations of your process. Okay, and we'll be going over specific examples of that. Sorry, I lost my sound. So let's go ahead and take a look at those homework standards. Set you up for success, right? Let's see. Okay. So homework standards. Sorry, technical issues. So pretty straightforward. I mean, just basically being clear and neat. Use engineering computation paper. That's that graph paper that we talked about earlier. Right on one side of the page only, easier to scan and send. Of course, this being an online course, everything we're submitting is digital. Use a pencil. Erasures shall be neatly done. And please try to write darkly enough that your scans come through, or your images come through legibly. So the pages have to be numbered. We'll take a look at that. Clearly identify the problem number, summarize the problem statement. Always draw and label a sketch for every problem using a straight edge and compass. So that's why we're getting the straight edge and compass. They really make it easier to draw your sketches, not necessarily to scale, but you can convey your ideas much more clearly. If you're using straight edge and compass, comes out much neater. I can read it much more easily. And then clear this, clearly show. So always draw and sketch for every problem. Clearly show the solution in a stepwise method. A good presentation doesn't require the reader to hunt for each step of the process. I mean, I shouldn't have to jump around, the page top to bottom, side to side to try to track what your process is. So use lots of paper. Don't try to cram things into little tiny spaces. I'd rather have 10 pages for one problem than 10 pages or 10 problems in one page. And then clearly indicate the answer using a double line. I actually prefer that you draw a box around it, circle it, make it very clear. So here's an example. Has the assignment and a date. The course, this says 161. Of course, we're in 163. Your name, please put your full name. And then the page number, let's see, the page number, and then out of however many pages. So 1 out of the total number of pages, 1 out of 2 and 2 out of 2. That way, if something is lost or they get out of order, I just don't think you skipped a problem. It's really to your benefit to follow these. So as an example, here it states the given and what's required. Here's a nice sketch. Of course, your sketches will probably be a little more elaborate than this. This is a simple, just a simple example. And then clearly stated and very clear the solution in a stepwise fashion. And then the final solution is double underlined. Again, boxes are even better. Double underlines, it suffices. But just as long as your solution is clear and I don't have to hunt for it and guess, is this what you mean by the final solution, or, am I wrong? So that's, it's pretty straightforward, just as clear and concise as you can make your homework problems, the better. So in the past, and I think I will, no, I'm going to commit. I'm going to offer it again this term. For this level of a course, when you're trying to get used to what a professional submission looks like, it's helpful to have motivations. So each homework is worth a certain number of points. Excuse me. What I've done in the past, and it's worked out well, is I've offered subjectively up to 3 points of extra credit on each problem. Or not on each problem, sorry, on each homework. So that is completely up to my discretion. How neat is your submission? How clear is your submission? How good is your sketch? How adequate are the steps that you took? How consecutively did you present the steps that you took? So it's not an automatic. But hopefully to motivate you to try to follow the homework standards, because it is good practice. Again, 0 to 3 extra credit points. We all love, yay, extra credit, right? On each homework assignment based on my discretion. So those are the homework standards. Nothing should be surprising. I'm sure you're all going to just, submit really shiny, nice homework assignments. it just makes things a lot easier to grade. Make sure you're getting the points that you are deserving, and blah, 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 blah. Okay, so back to the syllabus. So lab projects. As I mentioned a couple times, this is a lab intensive course. So we get to work outside, and hopefully the weather will be accommodating. However, just know that be prepared. Sometimes you may have to go out in cold, wet weather, snowy weather. Hopefully not, but it's a possibility. So yeah, proper clothing. I don't think there's going to be any off-campus venues. For some courses there are. What else? Okay, so the field work will need to work in groups. So those of you that are on campus, the class will need to break out into groups of 3 or 4. Try to try to form your groups so that they are as successful as possible for all the people involved. A lot of you have surveying jobs outside of school, so you have more experience with total stations, field work, traversing, and a lot of you don't have as much experience in that area. So try to help each other out, form your groups so that everyone kind of fits each other's needs. All the teams work more successfully that way. Particularly if you have a lot of experience in this type of work, you tend to get a greater understanding from your experience if you can help other people who don't have the experience that you have. So yeah, let's see, already stated, you'll need field notebook, scientific calculator, engineer scale, flash drive for saving project data. I like to save my project data on a personal drive, whether it's an external hard drive or a flash drive. I know that you all have on-campus server storage for your data. You're certainly welcome to use that. I really strongly suggest you back up all of your data on your own flash drive you can take anywhere with you, or a hard drive of some kind. Let's see, we talked about exams. Again, this is an engineering course. Neatness is of critical importance. So be cognizant of your handwriting. Honestly, I'm going to tell you guys, if I have to work too hard at understanding your homework, I'm probably not going to work that hard because I have a lot of other things that I have to do for the course. I'm going to help you out as much as I can, but I also hope that you'll help me out as much as you can by making your homework problems and your lab submissions as understandable as possible. Number 2, equipment we use is really expensive and delicate, and it's in short supply. So please be careful with them. Incompletes, very rarely are incompletes offered. Well, we can have that conversation if something comes up. Sometimes things come up. I've had them come up before and had students request an incomplete so that they can finish the course later in the following term. It really just adds to problems. So we'll try not to do that, but again, we can have that conversation. And then all the boilerplate stuff, department mission statement. You can read through these. Classroom conduct. We're adults. Let's treat each other with respect and friendliness and respect, integrity. So academic integrity. Again, boilerplate stuff. Don't cheat. It's not worth it. Plagiarizing, cheating, not worth it. And again, more boilerplate stuff. You can read through this when you need to or when you'd like to. So that's pretty much it. I just wanted to take a couple minutes. I took quite a few minutes, but just to kind of glance through the syllabus and set up objectives. So we are going to have regular weekly Zoom sessions. I sent out emails about that. If those evenings don't work for you, don't worry about it. Zoom sessions are not required. Think of them like office hours. If you're not able to make the regularly scheduled Zoom sessions, certainly reach out to me. We'll schedule more. I will make time, I promise. And with that, up here at the top of the syllabus is my phone number and my email. I respond to everything. I have yet to ever not respond to an email. And I especially have yet to not respond to an email in a timely manner. So I usually am able to respond to emails, within the day. Most often it's within minutes or an hour. Please be advised that my other career, I am out of cell range quite a bit. So if you text me or email me through the day and I don't get back to you until later the afternoon or the evening, it's only because I'm out of cell range and I'm not getting any kind of information or communications. So with that, let's get started route surveying. If you have any questions about anything we've gone over or anything in the syllabus, please reach out. So yeah, let's do this. Let's go. So first of all, let's take a quick gander at the good old Canvas. This is where I'm sure you've seen this before. I know Oregon Tech uses this format extensively. Let's take a quick look at the layout a little bit. First of all, at the top here, there's a library. So in the library is where I'm going to put just various reference materials that you'll want to be using throughout the term. Campus Control is the book that has coordinates and information about monuments set throughout the Oregon Tech campus for those of you that are taking the course on campus. That's what you'll use to get the primary control for your layout. And then the NCSS curve equations has the basic curve equations in one-stop shopping for horizontal curves and vertical curves. And then this little guy here, this HDD to HMS macro worksheet, it's going to be really useful. You may have used it in computations or in one of the plane surveying classes or both. But it's pretty cool. It's useful for doing what you're going to be doing continuously, which is going back and forth between decimal degrees and degrees, minutes, seconds formats of angles. And next time or the time after, we're going to talk a little bit about working with angular measurements, performing mathematics on angular measurements. It seems to be a topic that at first seems a bit abstract for students, so we want to get clear on that. But to use it, it's really simple. Let's say I have an angle of 45 degrees, 15 minutes, and 35 seconds. Just made that up. Okay. You enter it as full degrees, decimal point, and then the minutes and the seconds, 2 digits each. The cool thing about this, there's also, if you go up here to the more number formats and then go to custom, if you scroll down, you can actually change what it looks like. So it looks more like degrees, minutes, and seconds, which should be somewhere here. Maybe not. I'll have to add that later, but it's real easy to do. So that's in degrees, minutes, seconds. So degrees, minutes, seconds. if you wanted to convert that to decimal degrees so you could actually perform math on it, because you can't easily or readily perform math on angles when they're in degree, minute, and second format. That's called sexagesimal number base. It's a 60 base number system. We want it in a 10 base number system, so we want to put in decimal degrees. To do that, you just type equals for a function, HMS to, and you see it pops up there, HMS to HDD. And then you highlight that cell, close the parenthesis, and hit enter. So that is the decimal degree format. And now you can add, subtract, multiply, square. I don't know why we'd square an angle. And then to get it back to DMS, you just type the opposite, equals HDD for decimal degrees to, and there it is, to HMS to convert it back. And highlight the cell and close the parenthesis and hit it, and you get the degrees, minutes, seconds back. That's going to be really useful. You can use this over and over again. It's a template to perform various calculations, build elaborate spreadsheets for working with angles, incorporating distances into there. So remember that, and I don't want to save. Then after that, we'll have each week's class modules, lecture modules, as well as the lab modules. So that's just a brief rundown of how the Canvas is going to work. So let's talk about route surveying. What is route surveying? And a good place to start with that is, what is a route? And I just have to warn you, writing on this tablet has its problems. It's a little difficult. My handwriting isn't really good on this, but I'll try to make it clear. Drawings are particularly difficult, but we'll get through it. It really is a good tool. So a route is a way or a course taken from some starting point to some destination. Pretty simple. Nothing fancy there. Some examples of a route are a highway, a trail, maybe. What else? I mean, even, I don't know, a runway is a route. Of course, a railroad. And here's a fun one. This kind of blew me away when I first learned, but a pipeline is a route. And in fact, pipelines are administered and managed by the Department of Transportation, which we think of transportation as cars, trains, planes, but transportation is simply something that moves a thing or a person or something from one place to another. And that's exactly what pipelines do. They move oil from, or some kind of liquid, from one point to another. So pipelines fall under the Department of Transportation. So that's a route. And a route is made up of components. So I move this up. Nice thing about recorded lectures, you can pause it and perfect your notes. So components of a route. Essentially, I mean, routes can get very, very complex, but boiled down, there's three components of a route. So one is the planimetric component. Which is a bird's eye view. This is how you think of like a road map. You look down on a road map, bird's eye view, right? So you're seeing the horizontal representation of the road without really seeing gradients or hills, slopes, valleys, crests, just a bird's eye view of the horizontal layout. Okay. Another component is the profile, which is the other 3D perspective of a route. So a profile is, how do I put this? It is looking straight at the route horizontally from, and I'll put in quotes, ground level. So the planimetric, if I were to look straight down on a road, we would see the road, a curve, maybe another curve, and then out. And we would say there's a tree here, a tree here, a tree here. We're looking down on these trees. There might be a building here. The profile, on the other hand, is we're looking at it from ground level. So here's a straight slope up, slightly up, and then there might be a hill, and then it'll come down slope, and then a valley, and we might see a tree, my wonderful tree here, and a tree here, maybe a building down here, a nice house, chimney. So that kind of gives you some concept image of the difference between the planimetric view and a profile view. Finally, I won't move up too far. We have the topographic component. So the topographic, it's the overall characteristic put this of the ground. So the elements, some elements of the topographic component would be things like contours on a map, like on a USGS quadrangle, there's contours. That's an element of topography. What else? Let's see. That's where we would get data to calculate volumes and areas. We might calculate earthwork from the topographic data. So all three of those components taken together with all of their parts are what essentially make up the route, and how we use the route, or use those smaller details to design and communicate the elements of the route to other people. Important to note, these components are not mutually exclusive. That is, there's interplay between them. They are interdependent. Spell, Rob. Come on. Okay. So they're independent. So why don't we start at the beginning and look at the planimetric component. That's where we're going to spend most of our time over the next few weeks, is with the planimetric component. So planimetric. So we've all looked at maps, maps of trails, maps of roads, and when we look down, a road might look like a squiggle, right? Squiggle. But in reality, how we design routes and communicate the elements of routes is much more sophisticated. So in reality, a route is made up of straight lines. So I'm going to draw a straight line and curves, the most simple of which are circular curves. Okay, we're going to start out looking at circular curves, simple circular curves, horizontal curves, which you were introduced to in prerequisite courses. So, and then we need a way to define the straight line segment, the curved segment, and then another straight line segment, maybe, not very straight. And then maybe there's another curve, and there could be even, oh shoot, I don't know. That's real Bob Rossi of me. It's a compound reverse curve, right? A little more complex. That's just a compound curve is just two independent curves that are not separated by some tangent or not separated by some straight line. If I were to draw a curve and a straight line and then another curve, that would not be a compound curve. But if I were to get rid of that straight line segment and just do a curve and a curve, that's compound. If those curves are curving in the same direction, that is curving to the right or curving to the left, but they have different definitions, they would be kind of like that maybe, and then curve harder. That's a compound curve. A reverse curve is just a compound curve, a special case of a compound curve in which the curve changes direction. So of course, there are all kinds of curves. There are circular curves, which are the most simple. There are compound curves, reverse curves, and there are spiral curves. And we'll talk about spiral curves later on. Spiral curves are curves in which the radius of the curve is non-constant. So a circular curve has a constant radius throughout the curve. A spiral curve will actually have a decreasing curve into a circular curve, then a decreasing radius going into a circular curve, and then an increasing curve coming out, or increasing radius coming out. I'm going to keep doing that, switching my words. So how do we account for distances along a curve? So if I have some, let's consider a number line, just like baby pre-algebra back in 7th grade, or even, oh, what happened there? Sorry about that. Even back in elementary school, we talked about the good old simple number line. Right? There's a number line. And let me get rid of that. I can do a better number line than that. I have a little tool to do make a line straight. So there's a straight line. Unfortunately, it also makes it kind of faint. And on a number line, we have a 0. And then we have the points along the number line. Like so. And so we start with 0, and then we go to 1, 2, 3, 4, 5, etc. And what these numbers are actually distances, right? Here, I'm 1 unit away from 0. The beginning point. Here I'm 2 units away from 0. Here I'm 3 units away from 0. Well, we measure along center lines exactly the same way. We do it using a term called, or a method called stationing. Hopefully this is not new information. So stationing. Now with stationing, we're thinking of our center line as a number line. And conventionally, the American station method, using feet, one station, which from here forward is going to be STA, equals 100 feet. So if I had my beginning point, I'm using that term regularly, so beginning point, and then here I would have station 100, or at 100, and this one would be at 200, and here would be 300, so that there is 100 feet between each station. Right? Baby steps. Cool. Now the notation for stationing is awful. I hate it. It's very inconvenient, but it's engineering tradition. So at the 100 distance from, remember, stationing is a distance from some point of beginning, or POB, introducing some terminology here. Whereas the POB begins at station 0 plus 0, 0, which means 0, 100 and 0 feet. The first station would be at station 1 plus 0, 0. So at 100 and 0, 0 feet, and 2 plus 0, 0, 3 plus 0, 0, etc. Super easy. So that's how we talk about distances along a center line. So in effect, I'll change colors here because expansion on this idea. In effect, stationing along with offsets, which we'll talk about in just a second, sets up a grid system. If I wanted to define a specific point along a center line, in center line language, we don't necessarily stick to just northings and eastings. We have a different form of a grid system. So if I can draw a straight line here, it doesn't have to be horizontal, but it's easier to grid it out. Let's say I have, here's my 0. And over here I have 1 plus 0, 0, 2 plus 0, 0, 3 plus 0, 0. Let's say I wanted to define this point here, which is a perpendicular distance of 10 feet right of the center line. We're going to talk about the fact that center lines have direction. So right and left have meaning in terms of center lines. We can say that this is at station, this would be 1 plus 0, 0, then 2, 3, 4, 5, 6, 7 plus 0, 0, and this is actually halfway between. So this would be at 7 plus 50, and an offset of 10 feet right. That's how we use a center line as a grid system. Once we have our grid system, a center line also comes with the right-of-way. Right-of-way is nothing more than a line that is a certain distance on either side of the center line. Say, I don't know, 50 feet. So you can see how the center line is it's the bare bone of building a route. By the way, there's no reason why we must adhere to even stationing. So there's no reason why we have to stick to a 7+50 station. So let's say I have something that occurs at 1265.72 feet from the point of beginning, POB. Then it's real easy. That point is at station 12 plus 65.72. Okay. It's important to keep thinking of stationing as a distance. That's what stationing is. It's a distance. A lot of times people will get confused thinking it's just a point on the line. We can't really get from one point to the next, but it's useful if you want to talk about going from, say, station 2 plus 00 to 3, 4, 5 plus 00. Well, that's just, what's that distance? That's just 300 feet. It's the difference between 200 feet and 500 feet. So that's stationing. And while I'm on that topic, getting low on time here, it's astounding. Time is fleeting. Dumb joke, sorry. What if I were to take my center line? There's my center line. Again, planimetric view, I'm looking straight down on it. And I were to actually bend it with a curve and then out. That's supposed to be a straight line. What happens to my stationing? So nothing happens to my stationing. If I had between my fingers a wire, and on that wire were a bunch of blue dots, and I were to bend that wire, would the distance between those blue dots change? Absolutely not. So stationing continues around curves while maintaining distance. So distance along curves is important. And it can get confusing when we start introducing, measuring between, say, I can measure, certainly I can set up an instrument here, change colors. I can set up an instrument here and measure a horizontal distance to here, couldn't I? So I have a horizontal distance there, but this point we still describe in terms of the stationing as it's relevant to the center line. Okay, all of this super basic. We're just going to keep building on it though, so I'm going to start simply. While I brought up right-of-ways, so let me build a center line here. Just a straight center line, okay? You've noticed that when you're on the freeway or on a road downtown or a highway, the right-of-way width will change, won't it? So say it comes along here like that, and then it'll come up here like that, and the road will widen. And then at some point it might narrow back down. So you'll see on the road plans that this might be a 50-foot width. And then at here at station, say 1 plus 0, 0, that's a 1 plus 0, 0. We have 50 feet. And then at station 1 plus 50, we have 100 feet. So what does that mean? How do we interpret that? Obviously, the road is widening from 50 feet, or the right-of-way is widening from a 50-foot on one side, I'm just talking about one side of the center line, to 100 feet. And that transition here occurs over how many feet? 1 plus 0, 0 to 1 plus 50, that's 50 feet. So it takes 50 feet to transition from the 50-foot right-of-way width to the 100-foot right-of-way width. That's how stationing is used along with offset values or width values. Okay, so that's, we talked about the American system wherein we measure full stations at 100 feet each. That's called a full station. A half station would be every 50 feet, right? In the metric system, we use the same method, but we represent it a little bit differently. In the metric system, I need to thinify that line. Just a moment. There. One full station equals 1,000 meters, or 1 kilometer. Now, instead of up here from the American system, we have 1,000 feet would be 10 hundreds plus 0, 0. In the metric system, we would have 1,000 plus 0, 0, 0 meters. Okay, same distance. Well, not the same distance because we're going from feet to meters. But when we're working in meters, 1,000 meters equals 1 plus 0, 0, 0 station. Okay? Pretty easy. Good thing to review because we'll get back to this concept, especially when we start introducing vertical curves. It can get a little dicey when we're trying to figure out how we're going to calculate the components. Anyway, that's it. Next time we're going to start breaking down the anatomy of a route, the straight lines and the curves, and actually construct how horizontal curves are calculated. So that's it. Have a great rest of your day.